When you look up at the night sky on a clear evening, you are participating in one of the oldest human activities. The same stars that guide your eyes upward tonight have been watched by countless generations before you. There is something deeply calming about this continuity, this unbroken thread of observation that stretches back through millennia. The act of stargazing requires nothing more than your willingness to look up, to let your gaze wander across that vast darkness punctuated by points of light, and to simply be present with what you see. The night sky is not a photograph. It is not static or frozen. It is a living field of light, constantly in motion, even though that motion occurs on timescales both impossibly small and incomprehensibly large. Every photon of starlight that reaches your eye has traveled through the vacuum of space, perhaps for years, perhaps for thousands of years, before arriving at this precise moment to be absorbed by the cells in your retina. You are not just seeing the stars. You are catching light that has been traveling toward you since before you were born. This is not something that requires understanding in order to appreciate. The beauty of stargazing lies partly in its accessibility. You do not need to know the names of constellations or the classifications of stellar types to find peace in the simple act of observation. The stars offer themselves to you without prerequisites, without demands. They ask only that you look up, and they reward that simple gesture with a view that has comforted and inspired humans since the beginning of our species. Tonight, we will explore some of the most calming aspects of stargazing, the facts and phenomena that make looking at the night sky one of the most naturally relaxing activities available to us. We will move slowly through these ideas, allowing each one the space it needs to settle into your awareness. There is no urgency here, no need to rush from one concept to the next. The stars have been there for billions of years, and they will continue to shine long after we are gone. We have all the time we need. Before we venture into the specifics of what we see when we look up, it helps to understand what happens to our own eyes when we step outside into the darkness. This process, called dark adaptation, is one of the most remarkable features of human vision, and understanding it can deepen your appreciation for the night sky while also helping you see more of what is actually there. When you first walk outside from a lit room into the darkness, the world seems almost impossibly dark. You might struggle to make out even nearby objects, but if you wait patiently, remaining in that darkness, something extraordinary begins to happen. Slowly, gradually, the darkness becomes less absolute. Stars that were invisible moments ago begin to appear. The outline of trees or buildings emerges from the blackness. Your vision is adapting, shifting modes to become sensitive to the faint light that surrounds you. This transformation happens through a complex chemical process in the cells of your retina. Your eyes contain two types of light-detecting cells. The cone cells, which are concentrated near the center of your vision, are responsible for color perception and fine detail in well-lit conditions. The rod cells, which are more numerous and distributed around the periphery of your retina, are extraordinarily sensitive to light but cannot perceive color. They are your tools for seeing in darkness. Under normal lighting conditions, your rod cells are essentially inactive. They contain a light-sensitive chemical called rhodopsin, and this chemical becomes broken down, or bleached, when exposed to bright light. In daylight, your rhodopsin is constantly being bleached faster than it can regenerate, so your rod cells remain dormant. But in darkness, something different happens. Without the constant bombardment of bright light, your body begins to regenerate rhodopsin. As the rhodopsin rebuilds in your rod cells, your eyes become progressively more sensitive to faint light. This process does not happen instantly. Your pupils dilate within seconds of entering darkness, opening wide to allow more light to reach your retina. This provides an immediate but modest improvement in your ability to see in low light. The real transformation, however, takes much longer. Your cone cells adapt to darkness fairly quickly, reaching their maximum sensitivity in about 7 to 10 minutes. But your rod cells, the ones that will ultimately allow you to see the faintest stars, take much longer to fully adapt. Complete dark adaptation of your rod cells can take anywhere from 20 to 40 minutes. And in some cases, expert observers report that their night vision continues to improve for up to an hour or more. This lengthy adaptation period explains why astronomers are so protective of their night vision. A single exposure to bright light, even for just a few seconds, can break down the rhodopsin you have spent the last half hour building up. This is why astronomical observations often use red light for illumination when necessary. Rhodopsin is not particularly sensitive to deep red light, so a dim red flashlight allows you to read star charts or adjust equipment without destroying your carefully cultivated dark adaptation. The process of dark adaptation is not something you can rush. It requires patience, a quality that pairs perfectly with the contemplative nature of stargazing. As you stand in the darkness, waiting for your eyes to adjust, you are also giving yourself time to adjust mentally. The hurried pace of daily life begins to slow. The concerns that seemed so pressing indoors start to feel less immediate. By the time your eyes have fully adapted to the darkness, your mind has often adapted as well, settling into a calmer, more receptive state. There is also a technique called averted vision that can help you see fainter objects in the night sky. Because your rod cells are concentrated away from the center of your retina, you can often see dim objects more clearly by looking slightly to the side of them rather than directly at them. This might feel counterintuitive at first. We are accustomed to looking directly at things we want to see clearly. But when stargazing, sometimes the best way to see something is to not look straight at it. Instead, you let your peripheral vision, with its greater concentration of light-sensitive rod cells, do the work. This technique of averted vision has a meditative quality to it. You must let go of the instinct to focus directly on what you wish to see. You must trust that by looking slightly away, by relaxing your gaze, the faint star or nebula will reveal itself. It is a practice in patience and in direction, in allowing things to come to you rather than forcing them into view. As your eyes adapt and you learn to use averted vision, the night sky transforms. Stars that were invisible when you first stepped outside gradually appear. The Milky Way, if you are far enough from city lights, emerges as a faint band of light stretching across the sky. The darkness becomes less empty, revealing itself as a canvas scattered with countless points of light. And all of this happens simply because you waited, because you allowed your eyes the time they needed to adjust to the darkness, because you were patient enough to let the night sky reveal itself to you. When we talk about the distances between stars, we quickly leave behind the familiar units of measurement. Miles and kilometers become absurdly inadequate when describing the vast separations between stellar objects. A star that is merely 50 trillion miles away would require writing out a number with 14 digits. Even thinking about such distances in conventional units becomes an exercise in incomprehensibility. This is why astronomers use a different unit of measure: the light year. Despite its name, a light year is not a unit of time. It is a unit of distance, specifically the distance that light travels in 1 year. And because light moves at a fixed speed through the vacuum of space, approximately 186,000 miles per second, or about 300,000 kilometers per second. This gives us a consistent and meaningful way to express cosmic distances. To understand how far a light year actually is, consider this. Light travels at such extraordinary speed that it can circle the Earth more than 7 times in a single second. In 1 second, light covers 186,000 miles. Yet even at this tremendous velocity, it takes light about 8 minutes to travel from the Sun to Earth, a distance of roughly 93 million miles. This Sun-Earth distance, called an astronomical unit, serves as a stepping stone to understanding larger distances. 1 light year equals approximately 5.88 trillion miles, or about 9.46 trillion kilometers. To put this in perspective, if we were to measure distances in astronomical units, 1 light year would equal about 63,241 times the distance from the Earth to the Sun. These numbers are so large that they strain comprehension, which is precisely why the light year as a concept becomes so useful. Instead of dealing with numbers that have 13 or 14 digits, we can simply say that a star is 4 light years away or 100 light years away, and these numbers become manageable, even though the distances they represent remain almost incomprehensibly vast. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, located about 4.24 light years away from us. This means that the light you see from Proxima Centauri tonight left that star just over 4 years ago. You are not seeing Proxima Centauri as it is now, in this moment. You are seeing it as it was 4 years and 3 months ago. If Proxima Centauri were to suddenly vanish this instant, we would not know about it for another 4 years. The light already traveling toward us would continue its journey, still carrying the image of a star that no longer exists. This idea that we are always looking into the past when we look at stars adds a profound dimension to stargazing. Every star you see in the night sky is showing you its past. The brighter stars, the ones most visible to the naked eye, are generally closer to us, so their light might be only a few years or decades old. But some of the fainter stars you can see, and certainly the stars visible through telescopes, might be showing you light that left them hundreds or thousands of years ago. The North Star, Polaris, is approximately 433 light years away. When you use Polaris to navigate, you are navigating by light that left that star in the late 1500s, around the time Shakespeare was writing his early plays. Betelgeuse, the bright red star in Orion's shoulder, lies roughly 640 light years distant. The light you see from Betelgeuse tonight began its journey toward Earth in the 1380s during the Middle Ages. And these are relatively close stars by cosmic standards. This temporal displacement, this perpetual looking into the past, has a calming quality to it. It reminds us that the universe operates on timescales that dwarf human concerns. The light that reaches your eye tonight has been traveling for years, perhaps centuries, utterly indifferent to human events. Wars have been fought, empires have risen and fallen, entire civilizations have come and gone, all while this light continued its steady journey through the void. The stars connect us to the past not through memory or history, but through the actual physical presence of ancient light. There is also something reassuring about the fact that light has a speed, that it takes time to cross space. It means that the universe has a certain stateliness to it, a refusal to be hurried. Information, in the form of light, can only travel so fast. This sets a fundamental limit on how quickly things can change across cosmic distances. When you look at a star 10 light years away, you are guaranteed to be seeing it as it was 10 years ago. There is no way to see it as it is now. The universe enforces a mandatory patience on us, a built-in delay that prevents us from experiencing everything simultaneously. Some people find the vast distances between stars to be isolating or even frightening. They see the enormous gulfs of empty space and feel small or alone. But there is another way to view these distances. The fact that we can see light from stars thousands of light years away means that we are connected to those stars, even across that vast distance. The photons that left a distant star centuries ago have traveled all that way specifically to reach your eye tonight. In a very real sense, when you see a star, you are in contact with it. You are directly experiencing something that began its journey long ago and far away, something that has crossed the unimaginable emptiness of space to deliver its light to you. The light year then becomes more than just a unit of measurement. It becomes a way of thinking about time and distance as intertwined concepts. It reminds us that in the universe, there is no such thing as seeing something right now if that something is far away. Distance creates time lag. The farther away something is, the further into its past we see. And this is not a limitation or a flaw in our observations. It is simply how the universe works. Light takes time to travel, and that fact shapes everything about how we experience the cosmos. When you look up at the night sky and see the familiar patterns of constellations, you are seeing an illusion. Not in the sense that the stars are not there, they most certainly are, but in the sense that the patterns they form are products of perspective of our particular viewpoint here on Earth. The stars that make up any constellation are not actually close to one another in space. They are scattered across vast distances, separated by light years, with no physical connection to one another except the accident of how they appear from our vantage point. Consider the constellation Orion, one of the most recognizable patterns in the night sky. The stars that mark Orion's belt, those three bright stars in a nearly straight line, appear to be evenly spaced and closely associated, but in reality they lie at vastly different distances from Earth. Alnitak, the easternmost star in the belt, is approximately 815 light-years away. Alnilam, the center star, is about 1,340 light-years distant, and Mintaka, the western star, lies around 900 light-years from us. These stars appear to form a line only because of the particular angle from which we view them. In three-dimensional space, they are separated by hundreds of light-years. The same is true for every constellation in the sky. The Big Dipper, the Southern Cross, Cassiopeia, all of them are two-dimensional projections of three-dimensional arrangements. The stars that make up these patterns might be hundreds of light-years closer to or farther from us than their neighbors in the pattern. Some of the faintest stars in a constellation might actually be among the closest, appearing dim simply because they are intrinsically less luminous. Some of the brightest stars might be extraordinarily distant, appearing bright only because they are so enormously powerful that their light reaches us even across hundreds or thousands of light-years. This three-dimensional reality of star positions means that the constellations we see are unique to our location in space. If you could travel far enough away from Earth, the familiar patterns would begin to change. The stars that appeared close together would separate. The neat geometric shapes would distort. After traveling just a few light-years, the night sky would start to look unfamiliar. After traveling tens of light-years, the constellations would be almost completely unrecognizable. However, and this is the remarkable part, if you were to travel to Mars or Jupiter or even to the outer edges of our solar system, the constellations would look almost exactly as they do from Earth. This is because the solar system, despite its vast size by human standards, is tiny on the scale of interstellar distances. The distance from Earth to Pluto, at its farthest, is about 40 astronomical units, or about 3.7 billion miles. This sounds enormous, and it is by the standards of our daily experience. But compared to the distances to even the nearest stars, it is negligible. Proxima Centauri is more than 268,000 times farther from us than Pluto is. The change in viewing angle caused by moving from Earth to Pluto is so small, relative to stellar distances, that the constellations would appear essentially unchanged. This means that all the planets in our solar system share the same view of the stars. An observer on Mars sees the same Orion, the same Big Dipper, the same Cassiopeia that we see from Earth. This gives us a strange connection to these distant worlds. When we look up at the stars, we are seeing the same patterns that would be visible from any planet orbiting our Sun. The constellations are, in a sense, the common heritage of our solar system, a shared sky that ties together all the worlds that circle the same star. There is also a temporal dimension to this illusion of fixed patterns. The stars are not actually fixed in space. Each star has its own motion through the galaxy, traveling at speeds that can reach tens or even hundreds of kilometers per second. However, because the stars are so far away, these motions are generally imperceptible on human timescales. The constellations we see tonight look the same as they did 1,000 years ago, and they will look essentially the same 1,000 years from now. But over longer timescales, measured in tens or hundreds of thousands of years, the star's individual motions will gradually reshape the familiar patterns. Astronomers can calculate what the constellations looked like in the distant past and what they will look like in the far future by measuring the velocities of individual stars. The Big Dipper, for example, looked different 100,000 years ago, and it will look quite different 100,000 years from now. The stars that form its distinctive shape are moving in different directions at different speeds, and over such vast timescales, this motion is enough to distort the pattern significantly. But on the timescale of human civilization, the constellations are effectively eternal, changing so slowly that each generation sees essentially the same sky as the generation before. This constancy, despite the underlying motion and the illusory nature of the patterns, provides a sense of stability and continuity. The same stars that guided ancient sailors guide modern ones. The same patterns that inspired myths and legends thousands of years ago are still visible in the sky tonight. When you look up and see Orion's belt, you are seeing the same pattern from essentially the same perspective as someone who looked up from this same spot on Earth 1,000 years ago or 5,000 years ago. The constellations connect us not just to the stars themselves, but to all the generations of humans who have looked up and seen these same patterns. And yet, despite this constancy, despite the familiarity of these patterns, they remain fundamentally illusory. The stars in any constellation are almost certainly not physically related to one another. They formed in different places at different times, and they will continue their separate journeys through the galaxy regardless of how we perceive them, from Earth. The patterns we see are accidents of perspective, created by the particular location from which we view the cosmos. This does not make them less beautiful or less meaningful. If anything, it makes them more so, because it reminds us that the universe does not organize itself for our benefit. The constellations are not designs. They are the result of our pattern-seeking minds finding order in the random distribution of stars visible from our small planet. This interplay between pattern and randomness, between constancy and change, between the illusion of two-dimensional shapes and the three-dimensional reality of stars scattered through space is part of what makes stargazing so endlessly fascinating. The more you learn about the actual positions and motions of stars, the more remarkable it becomes that the sky appears so stable and ordered when viewed from Earth. The constellations are simultaneously real and illusory, constant and changing, meaningful and arbitrary. They are exactly what they appear to be when you first look up, patterns of bright dots in the darkness, and they are also vastly more complex and strange than they first appear. If you watch a star carefully on a clear night, you will notice that it twinkles. This twinkling, which astronomers call scintillation, is one of the most familiar and charming aspects of stargazing. It is also a phenomenon that tells us a great deal about our atmosphere and the journey that starlight takes before reaching our eyes. Understanding why stars twinkle and why planets generally do not adds another layer of appreciation to the simple act of looking up at the night sky. Stars do not actually twinkle. In the vacuum of space, starlight travels in straight, unwavering beams. If you were to observe stars from the International Space Station, or from the Moon, or from any location above Earth's atmosphere, you would see them shine with perfectly steady, constant light. The twinkling that we see from Earth's surface is entirely an effect of the atmosphere through which the starlight passes before reaching our eyes. Earth's atmosphere is not uniform. It consists of layers of air at different temperatures and densities, and these layers are constantly in motion, stirred by winds and convection currents. When light passes from one medium to another with a different density, it bends. This bending of light is called refraction, and it is the same phenomenon that makes a straw appear to bend when you place it in a glass of water. In the atmosphere, starlight undergoes refraction many times as it passes through the various layers of moving air between the star and your eye. Because the air is constantly moving and shifting, the path that starlight takes through the atmosphere is constantly changing. Sometimes the refraction bends more light toward your eye and the star appears momentarily brighter. A fraction of a second later, the air has shifted, the refraction changes, and less light reaches your eye, causing the star to appear dimmer. These rapid fluctuations in brightness, happening several times per second, are what we perceive as twinkling. The effect is much more pronounced for stars near the horizon than for stars directly overhead. This is because light from a star near the horizon must travel through a much longer path of atmosphere to reach you than light from a star overhead. More atmosphere means more refraction, more turbulence, more bending of the light path, and therefore more dramatic twinkling. On some nights, stars near the horizon can appear to flicker quite strongly, sometimes even seeming to change color as the varying atmospheric refraction affects different wavelengths of light differently. Blue light refracts more strongly than red light, so sometimes a twinkling star near the horizon will flash between slightly bluish and slightly reddish hues as the atmospheric conditions rapidly change. Planets, for the most part, do not twinkle. This is not because the light from planets is fundamentally different from starlight. Planets are visible only because they reflect sunlight, which is the same light that comes directly from stars. The difference is one of apparent size. Stars are so extraordinarily far away that even through powerful telescopes, they appear as mathematical points, infinitesimally small sources of light. Planets, being much closer to Earth, appear as small disks when viewed through a telescope. Even to the naked eye, although we cannot resolve this disk shape consciously, planets present a slightly extended source of light rather than a single point. This extended nature of planetary light makes a significant difference. When atmospheric turbulence causes the light path to shift, different parts of the planet's disk are affected differently. What would cause a star to flicker, a momentary reduction in light along one path, is compensated for by light from other parts of the planet taking slightly different paths through the atmosphere. The rapid fluctuations in brightness that would occur for a point source average out across the small disk of a planet, resulting in much more stable, steady light. Jupiter, Saturn, Mars, and Venus all shine with a relatively calm, unwavering light compared to the twinkling of stars. This difference between twinkling stars and steady planets provided one of the ways that ancient astronomers distinguished planets from stars before the invention of the telescope. The word planet comes from a Greek word meaning wanderer, because the planets slowly change their positions relative to the fixed stars over nights and weeks. But even on a single night, careful observers could tell planets from stars by the quality of their light. A bright object that shines steadily is likely to be a planet. A bright object that twinkles is almost certainly a star. The atmospheric conditions that cause twinkling vary from night to night and from place to place. On nights when the air is calm and the temperature is relatively uniform from the ground up to the top of the atmosphere, stars will twinkle less. On nights when the air is turbulent, when cold fronts are moving through, or when there are strong winds aloft, stars will twinkle more dramatically. Astronomers who need steady viewing conditions for detailed observations will check the weather forecast not just for clouds, but for atmospheric stability. A clear night with turbulent air can be less useful for detailed astronomical observation than a slightly hazy night with calm, stable air. There is something inherently soothing about watching stars twinkle. The rapid, random fluctuations create a sense of gentle animation in the night sky. The stars are not static points, but living, flickering lights, each dancing in its own rhythm. The twinkling reminds us that we are looking at these distant suns through a dynamic, moving atmosphere, that the light has taken a journey to reach us and has been shaped by that journey. It connects the far reaches of space to the here and now, to the air currents moving above your head, to the temperature differences that exist in the miles of atmosphere between the ground and the edge of space. And there is a particular beauty to twinkling stars near the horizon, especially on cold, clear nights when the atmosphere is most turbulent. These stars can seem to flash and sparkle with unusual intensity, sometimes displaying brief flickers of color as the atmospheric refraction separates the different wavelengths of starlight. It is as if the stars are signaling to you across the vast distances, their steady light transformed by our atmosphere into something more animated, more lively. The twinkling is not a distortion or an error. It is a reminder that we view the universe through a lens, through this envelope of air that surrounds our planet, and that this lens has its own character and its own effects on what we see. The very fact that stars twinkle tells us something profound about our planet. It tells us that we have an atmosphere, that we are surrounded by air, and that this air is in constant motion. Astronauts looking at Earth from the International Space Station cannot see the atmosphere directly. It is transparent, but they know it is there. And one of the ways they know is that when they look down at Earth and see city lights below them, those lights twinkle just as stars do when viewed from the ground. The twinkling is evidence of the atmosphere, proof of the dynamic, turbulent ocean of air through which we live and through which we view the cosmos. While you stand still on the surface of the Earth, looking up at the seemingly motionless stars, you are actually moving at extraordinary speeds. The Earth itself is in constant motion, both rotating on its axis and orbiting around the Sun, and these motions carry you along at velocities that would seem impossible if we could somehow perceive them directly. Yet, we feel none of this motion. The stillness we experience when we stand and gaze at the stars is an illusion, a consequence of the fact that we are moving along with everything around us. The Earth rotates once on its axis approximately every 24 hours. This rotation speed varies depending on your latitude. At the equator, where the Earth's circumference is greatest, the surface is moving at about 1,000 miles per hour, or roughly 1,600 kilometers per hour. This is faster than commercial aircraft fly. At mid-latitudes, such as at 45 degrees north or south, the rotation speed drops to about 730 miles per hour. At the poles, the rotation speed is effectively zero. You would simply spin in place once every 24 hours without covering any distance. This rotation speed of 1,000 miles per hour at the equator is remarkable, yet we do not feel it. We do not feel it because everything around us is moving at the same speed in the same direction. The air, the ground, the trees, the buildings, your car, your clothes, your body, all of it rotates together with the Earth. There is no relative motion between you and your surroundings to create the sensation of movement. It is similar to riding in a smoothly moving car on a perfectly level road. If you close your eyes, you cannot tell whether the car is sitting still or traveling at a constant 60 miles per hour because everything inside the car is moving together. There is no acceleration, no change in speed or direction to produce a sensation of motion. The Earth's rotation is extraordinarily constant. It does not speed up or slow down noticeably within human timescales. Over very long periods, tidal forces from the moon are gradually slowing the Earth's rotation, making days slightly longer. 600 million years ago, a day was about 21 hours long. But this change happened so slowly that it is completely imperceptible to us on any human timescale. The Earth's rotation is effectively unchanging, spinning at the same rate day after day, year after year, century after century. In addition to rotating on its axis, the Earth is also orbiting the Sun. This orbital motion happens at a speed of approximately 67,000 miles per hour, or about 107,000 kilometers per hour. To put this in perspective, the Earth travels roughly 18.5 miles every single second. In the time it takes you to read this sentence, the Earth has moved tens of miles along its orbit. In one day, the Earth travels approximately 1.6 million miles through space as it follows its elliptical path around the Sun. This orbital speed seems even more impossible than the rotation speed, and yet we feel none of it. Again, this is because everything we experience is moving along with us. The entire solar system is traveling together through space. The Earth, the Moon, the other planets, the Sun itself, all of them, are moving through the galaxy as a single unit. There is no wind rushing past us, no sense of acceleration, because we are in what physicists call free fall. The Earth is constantly falling toward the Sun, but because it is also moving sideways at just the right speed, it falls in a curve that takes it around the Sun rather than into it. This continuous falling creates an orbit, and being in orbit means being in free fall, which means feeling no sensation of motion at all. The speeds at which the Earth moves have another consequence that is directly relevant to stargazing. As the Earth orbits the Sun, our perspective on the stars changes very slightly. Over the course of 6 months, we move from one side of our orbit to the other, a distance of about 186 million miles. This change in position is enough to create a tiny but measurable shift in the apparent positions of the nearest stars, an effect called parallax. By measuring this parallax, astronomers can calculate the distances to nearby stars. This technique provided some of the first reliable measurements of stellar distances in the 19th century and remains an important tool for mapping our cosmic neighborhood. But for casual stargazing, the orbital motion of the Earth has a different, simpler effect. As we orbit the Sun, different parts of the sky come into view at different times of year. The stars that are visible in the evening sky in January are different from the stars visible in the evening sky in July because we are looking out in different directions from different points in our orbit. The seasonal progression of constellations is a direct result of the Earth's orbital motion. Orion dominates the winter sky in the northern hemisphere because in winter, the Earth has moved to the part of its orbit where Orion is visible in the evening. 6 months later, in summer, the Earth has moved to the opposite side of its orbit, and Orion is behind the Sun from our perspective, invisible in the bright daytime sky. This changing view of the stars throughout the year is one of the pleasures of stargazing. Each season brings its own constellations, its own pattern of stars. There is always something new to see, simply because the Earth's motion carries us to a new vantage point from which we view the cosmos. The night sky is not static, but cycles through variations that repeat annually, like a cosmic clock marking the passage of time. There is something deeply calming about the Earth's motion through space when you really contemplate it. We are passengers on a planet that moves at tremendous speeds, yet that motion is so smooth and constant that we experience it as perfect stillness. We rotate at 1,000 miles per hour and orbit at 67,000 miles per hour, and we feel none of it. The stars appear fixed and motionless in the sky, drifting only slowly across the night as our rotation carries us from sunset to sunrise. This is the universe. This is operating at scales and speeds that transcend our everyday experience, and yet we can observe it simply by standing still and looking up. The fact that we do not feel the Earth's motion also provides a form of stability. Despite the enormous speeds involved, our experience is one of being anchored, grounded, secure. The ground beneath your feet is solid and unmoving from your perspective, even though in absolute terms it is racing through space at velocities that exceed anything we can achieve with our fastest spacecraft. This disconnect between the reality of motion and the experience of stillness is one of the elegant features of the universe, a natural consequence of the principles of relativity that govern how motion works. When you stand outside and look up at the stars, you can take comfort in this stability. The Earth's motion is not erratic or unpredictable. It follows precise mathematical laws, the same laws that have governed its motion for billions of years and will continue to govern it for billions more. The rotation that brings sunrise and sunset happens with such regularity that we can predict the exact time of sunrise on any future date thousands of years from now. The orbit that carries us around the Sun is so reliable that we can calculate the positions of planets centuries into the past or future with extraordinary precision. This reliability, this predictability, extends to everything we see in the night sky. The stars rise and set at times we can predict. The planets move along paths we can chart years in advance. The phases of the moon follow an unchanging cycle. All of this regularity exists because the motions that create these phenomena are governed by gravity, by the same universal law that holds you to the surface of the Earth, and gravity operates with mathematical precision. The universe is not chaotic or random in its large-scale motions. It is orderly, following rules that we can understand and predict. When you look up at the night sky far from city lights, one of the most striking features you might see is a faint, milky band of light stretching across the darkness. This is the Milky Way, the galaxy in which we live, seen from the inside. Understanding what you are actually seeing when you look at the Milky Way adds a profound dimension to the experience of observing it. The Milky Way galaxy is a vast collection of stars, gas, dust, and dark matter bound together by gravity. Current estimates suggest the galaxy contains somewhere between 100 billion and 400 billion stars. The uncertainty in this number might seem strange. How can we not know the number more precisely? But counting stars in our own galaxy is extraordinarily difficult because we are embedded within it. We can only observe the galaxy from our position inside it, and much of the galaxy is hidden from us by intervening clouds of dust. It is like trying to map a forest while standing in the middle of it. You can see some trees nearby clearly, but your view of distant parts of the forest is obscured by all the trees in between. The Milky Way is structured as a spiral galaxy with several major spiral arms curving out from a central bar-shaped concentration of stars. The galaxy is approximately 100,000 light-years in diameter, though recent measurements suggest it might be slightly larger, perhaps 180,000 light-years across, when you include its outer regions. The disk of the galaxy, where most of the stars reside, is relatively thin compared to its diameter, only about 1,000 light-years thick in the main disk, though it has a thicker central bulge. Our Sun, along with Earth and all the other planets in our solar system, is located roughly 26,000 light-years from the galactic center. We reside in a minor spiral arm called the Orion Arm or Orion Spur, positioned between two major spiral arms. Our location is neither central nor particularly remote. We are in the suburbs of the galaxy, about halfway from the center to the edge, in a relatively quiet neighborhood where stars are spaced at comfortable distances from one another. When you look at the Milky Way band stretching across the night sky, you are looking toward the plane of the galactic disk. The faint glow you see is the combined light of billions of stars that are too distant and too faint to see individually. Each star contributes a tiny amount of light, and when you add up the light from billions of stars, it creates this soft, diffuse glow. The Milky Way appears as a band rather than a uniform glow across the entire sky because we are viewing the galaxy from within its disk. When you look toward the plane of the disk, you see many stars. When you look perpendicular to the disk, up or down relative to the galactic plane, you see far fewer stars, so those directions appear darker. The brightest and densest part of the Milky Way, as seen from Earth, lies in the direction of the constellation Sagittarius. This is because Sagittarius lies in the direction of the galactic center. When you look towards Sagittarius on a summer evening from the northern hemisphere, you are looking toward the heart of the galaxy, where stars are most densely concentrated. This region of the Milky Way is particularly spectacular when viewed from dark locations, appearing as a bright, mottled band with complex structure, dark lanes created by intervening dust clouds, and bright patches where star density is particularly high. The dark lanes and patches visible in the Milky Way are not empty spaces. They are clouds of dust that block the light from stars behind them. These dust clouds are concentrated in the plane of the galaxy, and they create a complex, mottled appearance in the Milky Way band. Some of these dark regions have names. The Great Rift, for example, is a series of overlapping dust clouds that creates a dark lane running through the brightest part of the Milky Way. This dark lane divides the Milky Way into two separate streams of light when viewed from very dark locations. Our position within the galaxy means we can never see the Milky Way as it would appear from outside. We cannot observe its grand spiral structure directly, cannot see the elegant curve of its arms, or the bright glow of its central bulge from an external vantage point. What we see instead is a cross-section, a view from inside looking out through the layers of the galactic disk. Astronomers have mapped the structure of the Milky Way through careful observation and measurement, but the maps they create are educated reconstructions, not direct images. There is something humbling about this perspective. We live inside this enormous structure, this island of hundreds of billions of stars, and we can observe it only from our single vantage point within it. It is like being a single cell in a vast organism, aware that the organism exists, but able to perceive only the immediate surroundings. And yet, even from this limited perspective, the view is magnificent. The Milky Way band stretching across a truly dark sky is one of the most beautiful sights in nature, a reminder of the vast cosmic structure of which we are a tiny part. The Milky Way has been known to humans for as long as humans have looked up at the night sky. Ancient cultures around the world created myths and stories to explain this mysterious band of light. Some saw it as a river, others as a road or a path. The name Milky Way comes from Greek mythology, in which the goddess Hera spilled milk across the sky. The ancient Chinese saw the Milky Way as a river separating two lovers, represented by the stars Vega and Altair. These stories reflect the universal human impulse to find meaning and narrative in the patterns we observe in nature. It was not until the 17th century that Galileo, using one of the first telescopes, observed the Milky Way and realized that it was composed of countless individual stars. Before this, people did not know what the Milky Way was. It was simply a mysterious glow, clearly different from the distinct pinpoints of individual stars, but without clear explanation. Galileo's observation began the process of understanding that we live within a vast collection of stars, a realization that would eventually lead to our modern understanding of galaxies and the structure of the universe. The Milky Way galaxy is in motion, just as the Earth is in motion around the Sun. The Sun, along with the entire solar system, orbits the center of the galaxy. This galactic orbit takes approximately 225 to 250 million years to complete. The Sun has completed this orbit roughly 18 to 20 times since it formed 4.5 billion years ago. The orbital speed is approximately 514,000 miles per hour, or about 828,000 kilometers per hour. This is yet another motion that we cannot perceive directly, but it is real and constant, carrying us on a vast circle around the heart of our galaxy. The Milky Way itself is not static in the larger universe. It is moving through space along with all the other galaxies in what astronomers call the local group. The local group is a collection of more than 50 galaxies, including the Milky Way and the Andromeda Galaxy, all bound together by gravity. The Milky Way and Andromeda are actually moving toward each other and will eventually collide and merge, though this will not happen for approximately 4 billion years. But these vast motions and future events are far beyond the timescale of human experience. When you look up at the Milky Way tonight, you are seeing a structure that has existed in essentially its current form for billions of years and will continue to exist, at least in recognizable form, for billions more. The stars have changed, of course. Individual stars are born and die. But the overall structure of the galaxy is stable on timescales that dwarf not just human lifetimes, but the entire history of human civilization. This stability is comforting. The Milky Way you see tonight is the same Milky Way that was visible to people thousands of years ago, the same Milky Way that will be visible thousands of years from now. The particular stars within it may change very slowly over vast timescales, but the overall structure, the band of light crossing the sky, remains constant. You are seeing something ancient and enduring, something that connects you to the deep past and the far future. There is also something intimate about the Milky Way, despite its vast scale. It is our home galaxy. Every star you can see with the naked eye, without exception, is part of the Milky Way. The Sun is a member of this galactic community, one star among hundreds of billions. When you look at the Milky Way, you are looking at your cosmic neighborhood, at the structure within which the Sun was born, and within which, barring some catastrophic event, it will end its life billions of years from now. You are looking at the gravitational system that holds the solar system, that provides the context for the Sun's orbit, that determines the overall environment in which we exist. The best time to observe the Milky Way depends on your location and the time of year. From mid-northern latitudes, the brightest parts of the Milky Way are visible during summer evenings, when Sagittarius and the galactic center are above the horizon. The winter Milky Way, while still visible, is less bright and dramatic because during winter evenings, we are looking away from the galactic center toward the outer regions of the disk. From the southern hemisphere, the galactic center is visible during winter months, and observers there have an even more spectacular view because the galactic center passes nearly overhead. To truly see the Milky Way, you need to get away from light pollution. Even a small amount of artificial light can wash out the faint glow of the galaxy. In cities and suburbs, the Milky Way is often completely invisible, overwhelmed by the scattered light from streetlights, buildings, and vehicles. But travel to a truly dark location, far from cities and towns, and the Milky Way reveals itself in all its glory. Under such conditions, the Milky Way is not a faint, barely visible glow, but a prominent feature of the night sky, bright enough to cast faint shadows, complex enough to show dark lanes and bright patches, stunning enough to evoke an emotional response. Many people living in urban areas have never seen the Milky Way. They have spent their entire lives under skies too bright to reveal this fundamental feature of the night sky. For these people, seeing the Milky Way for the first time from a dark location can be a profound experience. It changes their understanding of the night sky, reveals that there is far more out there than the few dozen stars visible from the city. The realization that this band of light is actually billions of stars in our own galaxy, that we are seeing our cosmic home from the inside, adds intellectual depth to the visual spectacle. On a clear night, if you watch the sky patiently, you are likely to see a meteor, commonly called a shooting star. These brief streaks of light, appearing suddenly and vanishing within a second or two, have fascinated humans for millennia. Understanding what they actually are and where they come from reveals processes that connect the Earth to the broader solar system in ways that are both scientifically interesting and oddly comforting. Meteors are not stars at all. They are small pieces of space debris, usually fragments of comets or asteroids, that enter Earth's atmosphere at high speed and burn up due to friction with the air. The streak of light you see is not the particle itself, but the glowing trail of superheated air that the particle creates as it plunges through the atmosphere. The particle itself is often no larger than a grain of sand, sometimes no bigger than a small pebble. These tiny fragments of cosmic material create surprisingly bright flashes as they vaporize in the upper atmosphere. Earth moves through space at approximately 67,000 miles per hour as it orbits the Sun. When a piece of space debris encounters Earth moving at this speed, the collision occurs at tremendous velocity. Even though the debris is also moving, often in roughly the same direction as Earth, the relative velocities can range from 25,000 to 160,000 miles per hour. At these speeds, the friction between the particle and the atmosphere generates enormous heat, enough to vaporize the particle and ionize the surrounding air, creating the brief flash of light we call a meteor. Most meteors burn up completely at altitudes between 50 and 75 miles above Earth's surface. They never reach the ground. Only larger pieces, usually at least the size of a fist or larger, have enough mass to survive the passage through the atmosphere and reach the surface as meteorites. The vast majority of shooting stars are the death throes of tiny particles that pose no threat to anything on the ground. On any given night, from any given location, you might see several meteors per hour if you watch patiently. These are called sporadic meteors, and they represent the background population of debris that Earth encounters as it moves through the solar system. This debris is left over from the formation of the solar system or created by collisions between asteroids or the gradual disintegration of comets. It is spread throughout the solar system, and Earth continuously encounters it as we orbit the Sun. In addition to sporadic meteors, there are meteor showers, periods when the number of meteors increases dramatically. Meteor showers occur when Earth passes through the orbit of a comet. Comets, often described as dirty snowballs, are composed of ice mixed with dust and rocky particles. As a comet approaches the Sun, solar heating causes some of the ice to vaporize, releasing the dust and rocky particles. These particles continue to orbit the Sun along roughly the same path as the comet, creating a stream of debris along the comet's orbital path. When Earth's orbit crosses the orbit of a comet, we pass through this stream of debris, and the result is a meteor shower. During a meteor shower, you might see dozens or even hundreds of meteors per hour, all appearing to radiate from a single point in the sky called the radiant. The radiant is simply the perspective effect of Earth moving through a field of particles that are all traveling in roughly parallel paths. Just as railroad tracks appear to converge at a distant point, even though they are parallel, meteors in a shower appear to radiate from a single point, even though they are following parallel trajectories. The major meteor showers occur at the same time, each year because they are associated with specific comets, and Earth passes through those cometary debris streams at the same point in our orbit each year. The Perseid meteor shower, one of the most popular and reliable showers, occurs every August when Earth passes through the debris stream of Comet Swift-Tuttle. The Geminid meteor shower occurs every December and is associated with an asteroid called Phaethon. The Orionid meteor shower in October is created by debris from Halley's Comet. These annual meteor showers provide a reliable and predictable opportunity for stargazing. You can look up the dates of major meteor showers months or years in advance and plan to observe them. The predictability is comforting, a reminder that even apparently random events like meteors follow patterns and cycles that we can understand and anticipate. Each day, Earth accumulates approximately 48 tons of space debris. This might sound like an enormous amount, but spread across the entire surface area of the Earth, it amounts to an average of only about 200 grams per square kilometer. This constant gentle rain of cosmic material has been falling on Earth for billions of years since the planet formed. Some of the atoms in your body, some of the molecules that make up the air you breathe or the water you drink, arrived here as cosmic dust. You are, in a very literal sense, made partly of material that fell from space. This connection between Earth and the debris of the solar system is another way in which stargazing connects us to the cosmos. When you see a meteor streak across the sky, you are witnessing a tiny fragment of a comet or asteroid, material that has been orbiting the Sun for millions or even billions of years, finally encountering Earth and ending its journey in a brief flash of light. That particle might have been released from its parent comet centuries ago. It has traveled through the solar system, silent and dark and invisible, until the moment it intersected Earth's atmosphere and transformed into a momentary streak of brilliance. There is poetry in this transformation, in the way something so small and insignificant becomes briefly notable through the violence of its destruction. The meteor burns not because it wants to, but because it must, because the physics of high-speed atmospheric entry leave no other possibility. And in burning, it creates beauty, a fleeting reminder that space is not empty, that the solar system contains vast amounts of material left over from its formation, and that Earth moves through this material constantly. Watching for meteors is one of the most accessible forms of stargazing. It requires no equipment, just patience and a reasonably dark sky. You can lie on your back, look up, and wait. Some nights you will see many meteors. Some nights you will see few. But over the course of an hour spent watching the sky, you are almost certain to see at least a few shooting stars. Each one is a small gift, an unexpected flash of light that momentarily draws your attention and then vanishes, leaving only the memory. There is something meditative about watching for meteors. You cannot predict exactly when they will appear or exactly where in the sky they will be. You must simply watch and wait, keeping your attention on the sky, allowing your eyes to wander across the field of stars. In this state of relaxed attention, you become more aware of the sky as a whole, more attuned to subtle changes and movements. And then suddenly, a meteor appears, bright and swift, and for a second you track its motion before it vanishes. And then you return to watching and waiting. This rhythm of watching, seeing, and returning to watching has a calming quality. It is the opposite of the constant stimulation of modern life, where something is always demanding your attention. When you watch for meteors, you are choosing to give your attention to something that might or might not appear, something that is entirely beyond your control. You are practicing patience and acceptance. You are engaging with the natural world on its own terms rather than demanding that it conform to your expectations. When you look at a star in the night sky, you are seeing an object that has been shining for an enormous length of time. Stars do not flicker on and off. They do not shut down at night and restart in the morning. They burn continuously, fusing hydrogen into helium in their cores, releasing energy that radiates outward as light and heat. This process continues for millions or billions of years, depending on the mass of the star, with no interruption, no rest, no variation, except for slow changes over vast timescales. Our Sun, which is a fairly typical star, has been shining for approximately 4.5 billion years. It has enough fuel remaining to continue shining for approximately another 5 billion years before it exhausts the hydrogen in its core and begins to change. During all this time, the Sun has been remarkably stable. Its luminosity, the total amount of energy it radiates, has increased by about 30% over the course of its lifetime. But this change has occurred so gradually that on any human timescale, the Sun appears constant. More massive stars burn through their fuel more quickly and have shorter lifetimes. A star 10 times the mass of the Sun might live for only 20 million years. A star 100 times the mass of the Sun might live for only a few million years. These are still enormous timescales by human standards, millions of years of continuous burning, but they are brief compared to the lifetimes of smaller stars. Conversely, stars less massive than the Sun burn more slowly and live longer. A red dwarf star, with a mass only 1/10 that of the Sun, can burn for trillions of years, far longer than the current age of the universe. This means that when you look at stars in the night sky, you are almost certainly seeing Stars that have been burning for a very long time and will continue to burn for a very long time. The stars visible to the naked eye from Earth are generally relatively close to us, within a few thousand light years. Most of these stars are on what astronomers call the main sequence, meaning they are in the stable phase of their lives where they are fusing hydrogen in their cores, just as the Sun is doing. They are not newborn stars still forming, and they are not dying stars in their final stages. They are mature, stable stars in the prime of their lives. This stability is one of the most reassuring aspects of stars. They do not change noticeably within human lifetimes. The stars you see tonight are the same stars, appearing essentially identical to those that were visible to your great-great-grandparents. Barring the occasional supernova or other rare event, they will be the same stars visible to your great-great-grandchildren. The constancy of the stars provides a sense of permanence and continuity that is increasingly rare in our rapidly changing world. There is also comfort in knowing that most of the stars you see are still there, still shining. When you look at a star 100 light years away, you are seeing light that left that star a century ago, but in almost all cases, that star is still burning today. Still creating light, still radiating energy into space. Stellar lifetimes are so long that the century or two of light travel time for nearby stars is insignificant. The stars have not changed in that time. The light showing you the star's past is an accurate representation of the star's present. Only in rare cases do we see stars that no longer exist. Very massive stars, the ones that live for only a few million years, can end their lives in spectacular supernova explosions. When this happens, the star's core collapses and its outer layers are blown off in an explosion so bright that it can briefly outshine an entire galaxy. These supernova explosions are visible across vast distances. If a massive star went supernova 1,000 light years away, we would see it as a new star appearing in the sky, a star that brightened dramatically over the course of a few days and then slowly faded over weeks or months. When we observe such a supernova, we are seeing an event that occurred in the past, perhaps hundreds or thousands of years ago, depending on the distance to the star. The star itself is already gone. It has collapsed into a neutron star or black hole, or its outer layers have expanded into a glowing cloud of gas. But the light from the explosion is still traveling outward, still carrying the news of the star's death to distant observers. We see the star's destruction not when it happens, but when the light from that destruction reaches us. But supernovae from individual stars are rare. They occur in the Milky Way galaxy only a few times per century on average. Most stars do not end their lives this way. Most stars, including the Sun, will end more gently, gradually expanding into red giants, shedding their outer layers into space, and leaving behind white dwarf cores that slowly cool over billions of years. This gentler ending happens over such long time scales that it is not something we would ever witness as a sudden event. The star simply fades, growing dimmer and cooler over millions of years until it is no longer visible. The longevity of stars has implications for life. Earth has existed in a stable environment with a sun that has changed very little over billions of years, allowing life to evolve and diversify. The stability of the sun has been essential to this process. If the sun varied significantly in its output over short timescales, life on Earth would be much more difficult or perhaps impossible. The fact that stars burn steadily for billions of years creates stable environments around them, environments where planets can maintain relatively constant conditions over the vast and timescales required for complex life to evolve. This stability extends to the wider view of the galaxy. When you look at the Milky Way, you are seeing a structure that has existed for billions of years and will continue to exist for billions more. The individual stars come and go. New stars are constantly forming in gas clouds scattered throughout the galaxy, and old stars are constantly dying. But the overall structure persists, maintained by the gravity that binds the galaxy together and by the continuous cycle of stellar birth and death. There is a rhythm to this cycle, a sense of cosmic metabolism. Stars form from clouds of gas and dust. They burn for millions or billions of years. They die, returning material to space. That material mixes with the interstellar medium and eventually becomes part of new gas clouds from which new stars form. The process repeats endlessly, ensuring that even though individual stars are mortal, the galaxy as a whole continues, regenerating itself through this cycle. The atoms in your body are part of this cycle. The carbon, nitrogen, and oxygen that make up most of your mass were forged in the cores of stars that died before the sun formed. Those stars lived their lives, fused hydrogen into helium and helium into heavier elements, then returned those elements to space when they died. The gas cloud from which the sun and earth formed was enriched with these heavy elements, and eventually some of those atoms became part of your body. You are made of stellar material, recycled through multiple generations of stars, carrying within you the legacy of stellar alchemy that has been ongoing for billions of years. When you look up at the stars, you are looking at objects engaged in the same process that created the atoms of which you are made. Every star in the sky is fusing lighter elements into heavier ones, creating the chemical diversity that makes planets and life possible. The stars are not just beautiful lights in the darkness. They are furnaces of creation, nuclear reactors converting the simplest element in the universe into all the others, building the periodic table one fusion reaction at a time. This ongoing creation is slow and patient. Stars burn for millions of years to build up meaningful quantities of heavy elements. But they have all the time in the world, or rather, all the time in the universe. The stars do not hurry. They simply burn steadily and continuously, creating new atoms and releasing energy, following the same physical laws that have governed them since the first stars ignited shortly after the Big Bang. One of the most remarkable aspects of stargazing is its fundamental accessibility. Unlike many hobbies or activities, stargazing requires no special equipment, no training, no prerequisites of any kind. You need only to look up. This simplicity is part of what makes stargazing so universally appealing and so deeply human. It is an activity that has been available to every human who has ever lived, from our earliest ancestors to people living today, and it will remain available to every human who will ever live in the future. You do not need a telescope to stargaze. Telescopes are wonderful instruments that can reveal details impossible to see with the naked eye, but they are not necessary for a meaningful stargazing experience. Many of the most beautiful and profound sights in the night sky are visible without any optical aid. The Milky Way stretching across the sky, the slow motion of the stars throughout the night, the appearance of meteor showers, the changing positions of planets against the background stars, all of these can be observed and appreciated with nothing more than your eyes and your attention. In fact, for some types of observation, the naked eye is actually superior to telescopes. Telescopes magnify small areas of the sky, allowing you to see detail, but they sacrifice the big picture. The wide field view that your naked eye provides allows you to see relationships between different parts of the sky, to track the motion of meteors across large portions of the sky, to appreciate the Milky Way as a continuous structure stretching from horizon to horizon. These experiences are difficult or impossible with telescopic observation, which typically shows you a small circle of magnified sky against a black background. The act of stargazing also does not require any particular location beyond one with a reasonably dark sky. You do not need to travel to observatories or special viewing areas, though darker skies certainly improve the experience. Many celestial objects and phenomena are visible even from suburban locations with moderate light pollution. The moon, planets, bright stars, the brighter constellations, and even some meteor showers can be observed from most locations. Only when you want to see the faint details of the Milky Way or observe very faint deep sky objects do you truly need to seek out darker skies. There is a democratic quality to this accessibility. Stargazing does not favor the wealthy or the educated. It is available to anyone who can look up. A person living in a small village far from cities has access to darker skies than someone living in a mansion in a major metropolis. A child looking up for the first time has access to the same view as an astronomer with decades of experience. The stars make themselves available to everyone without discrimination. This universal accessibility has meant that stargazing has been a part of human culture throughout all of history. Ancient civilizations built monuments aligned with celestial events. They tracked the motions of planets and stars and developed sophisticated astronomical knowledge. Navigators used the stars to cross oceans. Farmers used celestial cycles to determine when to plant and harvest. Time itself was marked by the cycles of the moon and the sun. All of this was possible because everyone could see the sky, could observe the patterns, could participate in the shared human experience of looking up and finding meaning in what they saw. The meditative quality of stargazing is another aspect of its appeal. When you look up at the stars, you are doing something that naturally quiets the mind. The vastness of what you see puts ordinary concerns into perspective. The timescales involved, the distances, the ages of the objects you are observing, all of these dwarf human affairs and create a sense of calm detachment. Your problems, whatever they might be, seem smaller when considered against the backdrop of the cosmos. This is not to say that your problems are unimportant or that you should ignore them, but there is value in occasional perspective, in stepping back from the immediate and personal to consider the larger context. The stars provide this perspective automatically, simply by being what they are. You do not need to work to achieve this shift in awareness. It happens naturally when you spend time looking at the night sky with an open and receptive mind. There is also something inherently calming about the darkness itself. In our modern world, we are surrounded by constant light and constant stimulation. Darkness has become rare, something to be avoided or eliminated. But darkness is natural. For most of human history, night meant darkness, and people lived half their lives in dim starlight and moonlight. Our eyes evolved to function in low light conditions. Our psychology includes adaptations for functioning at night. When we eliminate darkness entirely through artificial lighting, we lose something important. Stepping outside at night and allowing your eyes to adapt to darkness is a form of sensory reset. The lack of visual stimulation in all but the direction you are looking creates a natural focus. Your attention is not being pulled in multiple directions by bright signs, screens, or lights. There is only the sky, dark and vast and peaceful, with its scattered points of starlight. This reduction in stimulation allows your mind to settle, to slow down, to enter a more contemplative state. The silence often accompanying stargazing contributes to this calming effect. Nights tend to be quieter than days, especially in rural areas far from traffic. The absence of visual and auditory stimulation creates an environment naturally suited to reflection and contemplation. You can hear your own breathing, the occasional sound of wind or nocturnal animals, but otherwise there is quiet. This quiet is not empty or boring. It is restful, a respite from the constant noise of daily life. Stargazing can be a solitary activity or a shared one. Both modes have their appeal. Solitary stargazing allows for deep personal reflection, for experiencing the night sky on your own terms without the need to explain or discuss what you are seeing. Shared stargazing creates opportunities for connection, for pointing out interesting objects to others, for teaching and learning, for experiencing wonder together. Both approaches are valid, and most people who stargaze regularly enjoy both at different times. The teaching aspect of stargazing deserves special mention. Showing the night sky to a child or to someone who has never really looked at it before can be a profound experience for both teacher and student. The child's wonder and excitement at seeing Saturn through a telescope for the first time, or learning that the fuzzy band of the Milky Way is actually billions of stars, or watching a meteor streak across the sky, this authentic response to the cosmos is infectious. It reminds those who have become more familiar with the sky why they found it fascinating in the first place. And yet, even without teaching or sharing, even without telescopes or special viewing locations, even without extensive knowledge of astronomy, stargazing offers value simply as an act of observation. Looking up at the stars is an end in itself. It does not need to lead anywhere or accomplish anything. It is enough simply to look, to see, to be present with what is there in the sky above you. Light is perhaps the most fundamental aspect of stargazing, the medium through which we receive all information about the universe beyond our immediate surroundings. Understanding something about the nature of light, about how it travels and what it carries, deepens appreciation for the simple act of seeing stars in the night sky. Light is a form of electromagnetic radiation, a wave of oscillating electric and magnetic fields that propagates through space at a constant speed of approximately 186,000 miles per second in vacuum. This speed, usually denoted by the letter c in physics equations, is one of the fundamental constants of the universe. Nothing can travel faster than light. This speed limit is built into the structure of space and time itself. Light can be thought of as both a wave and a particle, depending on how you observe it. When thinking about light traveling through space, the wave model is often more useful. Light waves are characterized by their wavelength, the distance from one peak of the wave to the next. Different wavelengths of light are perceived by our eyes as different colors. The longest wavelengths visible to human eyes are red, around 700 nanometers in length. The shortest visible wavelengths are violet, around 400 nanometers. This range of wavelengths, from red through violet, is what we call visible light. But visible light is only a tiny portion of the full electromagnetic spectrum. There are electromagnetic waves with wavelengths longer than red light, including infrared, microwaves, and radio waves. There are waves with wavelengths shorter than violet light, including ultraviolet, X-rays, and gamma rays. Stars emit radiation across this entire spectrum, but our eyes evolved to detect only the narrow range of wavelengths that penetrates Earth's atmosphere most effectively, and that is most abundantly emitted by the sun. When a photon of light leaves a star, it begins a journey that might last for years, centuries, or even millennia before it reaches Earth. During this journey, the photon travels through the near-perfect vacuum of space. In the vast emptiness between stars, there is almost nothing to interact with the photon. No air to scatter it, no material to absorb it, no obstacles to deflect its path. The photon simply travels in a straight line at the speed of light, maintaining its energy and wavelength, unchanging and unaffected by the passage of time. This journey through empty space is one of the most remarkable features of light. The photon that enters your eye tonight, triggering a chemical reaction in your retina that allows you to see a distant star, might have been traveling for 1,000 years. During that entire time, through all those centuries, the photon has been moving through darkness and emptiness, maintaining its trajectory with perfect fidelity, waiting for the moment when it would finally encounter something and end its journey. The fact that space is transparent to light, that light can travel for enormous distances without being absorbed or scattered, is what makes astronomy possible. If space were filled with absorbing material, we would not be able to see distant stars. The light would be blocked before it reached us. But space is almost perfectly empty, and the little material that does exist, mostly hydrogen and helium gas, is too diffuse to significantly affect visible light over the distances between nearby stars. This transparency means that when you look at a star, you are receiving a direct message from that star. The light has traveled across space, carrying information about the star that emitted it. The color of the light tells you about the star's temperature. The brightness tells you about its luminosity and distance. If you were to examine the light more carefully with a spectrograph, spreading it out into its component wavelengths, you would see dark lines at specific wavelengths where elements in the star's atmosphere have absorbed light. These absorption lines act as chemical fingerprints, telling you what elements are present in the star. All of this information is encoded in the light itself, in the electromagnetic wave that left the star and traveled through space to reach you. Light is not just illumination. It is a carrier of information, a way that the universe communicates across the vast distances that separate objects in space. When you see a star, you are not just receiving light. You are receiving information that has traveled across light years of space to tell you about something far away. The darkness between the stars is as important as the stars themselves. This darkness is not absolute. It contains a very faint background glow from various sources. There is starlight reflected off dust particles in interstellar space. There is light from very distant stars and galaxies, too faint to see individually, but present in aggregate. There is the cosmic microwave background, the afterglow of the Big Bang itself, though this is not visible to our eyes because it has been redshifted by the expansion of the universe into microwave wavelengths. But despite these various faint sources of light, space is fundamentally dark. It is dark because it is mostly empty and because light travels in straight lines. The photons emitted by a star spread out in all directions, becoming more and more dispersed as they travel farther from their source. By the time they have traveled a few light years, the photons are spread so thin that the space between them is vast. Most of space contains no photons from any nearby sources, just the occasional photon from a distant star or galaxy passing through on its way to somewhere else. This darkness is what allows us to see individual stars. If space were filled with glowing material, the sky would be uniformly bright and we would not be able to distinguish individual sources of light. The darkness of space, the vast empty regions between stars, is what creates the contrast that makes stars visible as distinct points against the black background. Darkness is not the absence of something important. It is a necessary condition for seeing the light that does exist. When you stand under the night sky, you are surrounded by this darkness. Above you, below you on the other side of the earth, in every direction, space extends into darkness punctuated by occasional stars. This three-dimensional field of darkness with embedded points of light is the universe on the largest scale. It is mostly empty, mostly dark, with matter and light concentrated into small regions separated by vast distances. This emptiness might seem lonely or disturbing, but it can also be peaceful. The universe is not crowded. There is space, enormous amounts of space, between objects. This separation means that the universe is a relatively safe place on large scales. Stars are so far apart that collisions between them are extraordinarily rare, even in the densest regions of the galaxy. Galaxies can pass through one another, and despite containing billions of stars each, the chances of any two stars actually colliding is minuscule because the spaces between stars are so vast. This safety through separation is another reassuring aspect of the cosmos. Despite the tremendous energies involved in stellar processes, despite the violence of supernovae and the intense gravity of black holes, these dangers are isolated. They affect their immediate surroundings but do not threaten objects light years away. The Earth orbits a stable star at a safe distance, in a relatively quiet region of the galaxy, protected by vast spaces from most cosmic hazards. The journey of light from star to eye is also remarkably direct. When you look at a star, you are looking along a straight line from your eye to that star, and the light is traveling the reverse path from the star to your eye. There is something satisfying about this directness. You are not seeing a reflected image or a scattered approximation. You are seeing actual photons that left the surface of the star and traveled in a straight line to reach your retina. Your visual connection to the star is as direct as the nature of light allows. This directness creates a sense of connection across space. When you see a star, you are in a very real sense touching it with your vision. The electromagnetic radiation that left the star has physically interacted with molecules in your eye, has been absorbed by cells in your retina, has triggered chemical and electrical signals that travel to your brain and create the sensation of seeing. The star has reached out across space and touched you, and you have received that touch and interpreted it. As we move toward the end of our journey through these relaxing facts about stargazing, it is worth reflecting on what we have explored and what it means to look up at the night sky with understanding and appreciation. We have considered many aspects of stargazing, from the physical processes that make it possible to the cosmic structures we observe when we engage in it. But beneath all the specific facts and phenomena is a more fundamental truth about what stargazing offers us. Stargazing is an act of connection, a way of placing ourselves within the larger cosmos. When you look up at the stars, you are acknowledging that you are part of something much bigger than yourself, something that existed long before you were born and will continue long after you are gone. This acknowledgement does not diminish you. If anything, it provides relief from the burden of believing that everything revolves around human concerns. The stars remind us that the universe is vast, ancient, and indifferent to our troubles, and there is a strange comfort in that indifference. The regularity and predictability of the night sky also provide a form of stability in an often chaotic world. The stars will be there tonight, tomorrow night, and every night after that, barring only the occasional cloud. The moon will continue its phases, waxing and waning in an unchanging 29.5-day cycle. The planets will continue their slow wanderings across the background of stars, following paths that can be predicted years or centuries in advance. This cosmic clockwork operates with a reliability that is increasingly rare in human affairs. We have learned that the distances involved in stargazing are so vast as to be almost incomprehensible, measured in light years that represent trillions of miles. Yet these distances do not prevent us from seeing the stars, from receiving their light, from being connected to them through the photons that have traveled across space to reach us. The universe is large, but it is not isolated. Light crosses the gulfs between stars, carrying information and creating connections. We have explored how our own eyes adapt to darkness, how the process of dark adaptation takes time and patience, but ultimately reveals a richer, more detailed view of the night sky. This need for patience, for allowing time for our vision to improve, parallels the patience required for stargazing itself. The best experiences come not from rushed observation, but from taking time, from settling into the experience, from allowing the sky to reveal itself gradually. We have considered the constellations, those familiar patterns that have guided humans for millennia, and learned that they are illusions of perspective, two-dimensional projections of three-dimensional arrangements. The stars in any constellation are not close to one another in space, but are scattered across vast distances, appearing close only from our particular vantage point. This reminds us that perspective matters, that how we see things depends on where we stand, and that the same configuration of objects can appear very different from different viewpoints. The twinkling of stars, which we now understand as an atmospheric effect rather than a property of the stars themselves, connects the distant cosmos to the immediate here and now. The turbulent air above us shapes how we see the stars, creating the gentle flickering that makes them seem alive and dynamic rather than static points. This atmospheric effect reminds us that we observe the universe through a medium, through the ocean of air that surrounds our planet, and that this medium has its own character and its own influence on what we see. We have pondered the fact that Earth is in constant motion, rotating at 1,000 miles per hour at the equator and orbiting the Sun at 67,000 miles per hour, yet we feel none of this motion because everything around us moves together. This shared motion creates an experience of stillness even as we race through space at velocities that dwarf anything we can achieve with our technology. The contrast between motion and stillness, between the reality of our movement and the experience of being stationary, is one of the elegant paradoxes of existence. The Milky Way, our home galaxy, stretches across the sky as a band of faint light, the combined glow of billions of stars too distant to see individually. We are embedded within this structure, seeing it from the inside, unable to observe its grand spiral form except through careful reconstruction. Yet even our limited view from within reveals something of the majesty and scale of the galactic structure of which we are a tiny part. We live in a galaxy of hundreds of billions of stars, and that galaxy is one of trillions in the observable universe, and this scale is humbling and awe-inspiring in equal measure. Meteors, those brief streaks of light that appear and vanish in seconds, connect us to the material of the solar system, to the debris left behind by comets and the fragments created by asteroid collisions. Each meteor is a tiny piece of space material, ending its journey in a flash of light as it burns up in the atmosphere. We are witnesses to the constant, gentle bombardment of Earth by cosmic debris, a process that has been ongoing for billions of years and that contributes material to our planet every single day. The stars themselves burn for millions or billions of years, maintaining the same basic appearance throughout spans of time that exceed human comprehension. This longevity means that the stars we see are almost certainly still there, still burning, still creating light and heavy elements through nuclear fusion. The constancy of stars provides a sense of permanence, a connection to the deep past and the far future. The stars our ancestors saw are the same stars we see, and they will be the same stars visible to our descendants for countless generations to come. We have appreciated the fundamental accessibility of stargazing, the fact that it requires no special equipment or training, only the willingness to look up and pay attention. This universal accessibility means that stargazing has been part of human experience throughout all of history and across all cultures. Everyone who has ever lived has had access to the night sky, has had the opportunity to look up and wonder at the stars. We share this experience across time and space with all of humanity. The nature of light itself, that it is electromagnetic radiation traveling at a fixed speed, carrying information from distant sources to our eyes, adds depth to the simple act of seeing a star. We are not just receiving illumination. We are receiving photons that have traveled for years or centuries through the vacuum of space. Photons that carry encoded within them information about the star that emitted them. Each photon is a messenger from the cosmos, and when it reaches our eye and is absorbed, the message is delivered and understood. The darkness between the stars, far from being empty or void, is a necessary condition for seeing the stars themselves. The contrast between the dark background and the bright points of light is what makes stars visible as distinct objects. Darkness is not absence, but presence. The presence of vast distances and nearly empty space that allow light to travel without obstruction and that provide the canvas against which stars shine. All of these facts and phenomena come together to create the experience of stargazing, an experience that is simultaneously simple and profound, accessible and mysterious, calming and awe-inspiring. When you step outside on a clear night and look up, you are participating in something ancient and universal. You are seeing what humans have always seen, the same stars and planets and moon that have been watched by countless generations before you. But you're also seeing something unique, filtered through your own perspective, your own understanding, your own emotional and intellectual response to the cosmos. No two people see the night sky in exactly the same way. Each stargazing session is unique, shaped by the particular conditions of the night, the state of your mind, the depth of your knowledge, the quality of your attention. This combination of universal and personal, of shared and unique, is part of what makes stargazing so valuable. It connects you to all of humanity through shared experience while also giving you space for individual contemplation and response. The stars are there for everyone, but they are also there specifically for you, in this moment, offering whatever you need from them. Sometimes that might be knowledge, sometimes beauty, sometimes perspective, sometimes just a quiet place to rest your eyes and your mind. As you continue your own stargazing journey, remember that there is no wrong way to do it. You can learn all the constellations and track the planets and calculate the distances to stars, or you can simply look up and enjoy the view without needing to name or measure anything. Both approaches are valid. Both offer value. The cosmos does not judge your level of knowledge or the sophistication of your observations. It simply offers itself to you, night after night, waiting for you to look up whenever you choose. The most important thing is simply to look, to step outside, to let your eyes adjust to the darkness, to turn your gaze upward and see what is there. Everything else, all the facts and understanding and appreciation, flows from this simple act of attention. The universe is always there, always available, always ready to reveal itself to those willing to look. We began this exploration by noting that when you look up at the night sky, you are participating in one of the oldest human activities. We can end by noting that you are also participating in one of the most enduring, one of the most universal, and one of the most fundamentally rewarding activities available to us. Stargazing costs nothing, requires nothing, demands nothing. It simply offers itself, freely and generously, to anyone who looks up. In our modern world of artificial lights and constant stimulation, of screens and notifications and endless demands on our attention, the simple act of looking at the night sky becomes even more valuable. It is a respite, a reset, a reminder that there are things beyond the immediate and the urgent, things that exist on time scales and distance scales that dwarf human concerns. The stars were there before we arrived, and they will be there after we are gone, burning steadily through the darkness, creating light and elements, following the laws of physics that govern the cosmos. When you feel overwhelmed by the pace of modern life, when you need perspective or calm or simply a break from the constant stimulation, you can go outside and look up. The stars will be there, patient and unchanging, offering their light across the vast distances of space. You can watch them for a few minutes or for hours. You can try to identify constellations or simply gaze without purpose. You can think about the distances and processes involved, or you can let your mind rest and simply experience the beauty of points of light scattered across darkness. There is no pressure to understand everything, no need to become an expert. The night sky welcomes casual observers and dedicated astronomers alike. It offers something to everyone, regardless of their level of knowledge or commitment. All it asks is that you look up, that you pay attention, that you allow yourself to see what is there. And what is there is magnificent. Hundreds of stars visible on a clear night from a reasonably dark location, thousands more revealed if you travel far from city lights. The moon in its phases, the planets in their wanderings, the Milky Way stretching across the sky, meteors that flash briefly and vanish, satellites crossing the sky in stately procession, the slow rotation of the celestial sphere as Earth turns beneath it. All of this is there, waiting for you every night. Before we part, I want to take a moment to thank you for joining me on this gentle journey through the facts and phenomena of stargazing. We have explored many aspects of the night sky together, from the biological processes that allow our eyes to see in darkness to the cosmic structures that create the patterns we observe. We have considered distances and timescales that strain comprehension, and we have found calm and perspective in contemplating them. I hope that these thoughts and facts have added to your appreciation of stargazing, that they have given you new ways to think about what you see when you look up at the night sky. But more than that, I hope they have encouraged you to actually go out and look up, to spend time under the stars, to experience directly the calm and wonder that come from observing the cosmos. Stargazing is not something that can be fully captured in words or explanations. It must be experienced. The facts I have shared can enhance that experience, can add layers of meaning and appreciation, but they cannot replace the simple act of standing under a dark sky and looking up at the stars. That experience is immediate and personal, available only to those who actually engage in it. So I encourage you to go outside tonight, or tomorrow night, or whenever the skies are clear. Find a place away from bright lights if you can. Give your eyes time to adjust to the darkness. Look up and see what is there. Think about the distances involved, the timescales, the physical processes, or do not think about any of that and simply enjoy the beauty of it. Either way, you will be participating in something ancient and valuable, connecting yourself to the cosmos and to all of humanity across time. If you found value in this exploration, if it added to your appreciation of the night sky, or encouraged you to engage more deeply with stargazing, I would be grateful if you would consider liking this video and subscribing to Nebula Nights. This channel exists to explore cosmic topics in a calm, thoughtful way, to provide information and perspective that can enhance your understanding and appreciation of the universe. Your support through likes and subscriptions helps make it possible to continue creating this content. But more importantly, your support helps build a community of people who find value in slowing down, in contemplating the cosmos, in seeking perspective through understanding. Every person who engages with these ideas, who goes outside and looks up at the stars with a deeper appreciation for what they are seeing, contributes to a culture that values thoughtfulness and wonder over constant stimulation and immediate gratification. Thank you for spending this time with me, for giving your attention to these ideas, for being willing to think slowly and carefully about the nature of the cosmos. The stars will be waiting for you tonight, just as they have been waiting for every human who has ever looked up. Go find them. Let them show you their light. Let yourself be present with the vastness and the beauty and the quiet majesty of the night sky. Until next time, may your skies be clear, your eyes be dark, adapted, and your sense of wonder be alive and well. Keep looking up.